if you take the light that comes from a star and pass it through a prism, then it will break up into its constituent parts. So a single beam of light that passes into a triangular prism, different colours will refract by different amounts, such that the red end of the spectrum will be refracted less than the blue end of the spectrum, and all the other colours in the middle will also appear like so to produce the continuous spectrum that we know from rainbows, etc. Now, if this light is coming from a star or a galaxy, then the pattern that we get on the screen is the traditional red, orange, yellow, green, blue, indigo and violet that we'd imagine, except for within it there are parts that are missing. So within the red, orange, yellow, green and blue, what we actually have are bits that appear to be missing. And these bits that appear to be missing are called absorption spectra. So I'm drawing these black lines that are superimposed. Now, these black lines represent energy that has been absorbed from the spectrum. Now we know that red photons have got less energy than yellow, orange, yellow, green, blue, all the way up to violet. So there is a range of energies represented by the colours. So a red photon will have a certain amount of energy. This photon at this particular colour would have another amount of energy. So you can think of this as a continuous spectrum of photon energies. And clearly some photons didn't make it to the Earth from the Sun. Now the reason for that is that the core of the Sun is where the fusion takes place and where the light is emitted, but the star itself is made of gas. So even though the light might be emitted from the core where fusion is taking place, as the photons are passing through the rest of the star, some of that photon energy is absorbed. So some photons are being absorbed by the gas in the star itself. Photons are absorbed by the gas in the star. So this idea is very, very useful to scientists because these particular patterns, known as Fraunhofer lines, after Fraunhofer who first investigated them, these patterns represent something particular about the gases within the star. Now, the reason that energy gets absorbed is because of electrons surrounding the nucleus of an atom. So if that's my nucleus there, my positive centre, and then surrounding that I have my electron shells, forgive the terrible drawing. For example, if a photon of energy comes along and it's the right amount of energy, i.e. it's the right colour, then this electron will absorb that photon and it will jump up to a higher energy state. Or in this case, the higher energy state is represented by an orbit that's further away from the nucleus. So you can think of electrons in this orbit have got more energy than these. So if just the right amount of energy to jump that gap comes along, then that electron can jump up. Or if a different amount of energy comes along, for example, for this one, a different colour, that can make it jump from there to there. Or it can jump from there to there, etc. But each one of these jumps requires a specific energy, and therefore that's a specific colour. So what these black lines show us, this absorption spectra, is where energy has been absorbed to allow electrons to jump to a higher energy state. Now, you can actually do the reverse of an absorption spectra and make a line spectra from any gas of any element. So if you take a gas in a gas jar or any other device, if you take a particular gas and you energize it by putting a large potential difference across it, then that gas will start to glow a particular colour. So for example, sodium street lamps will glow kind of orangey yellow. Now the reason they glow orangey yellow is because what's happening is the reverse of what's happening in my absorption spectra, which is that electrons are being energized by the energy that's given to them, and they are jumping up to higher energy states. But when they jump up to a higher energy state or a higher orbit, they're unstable, and therefore they fall back down again to their original place or to somewhere else. And as they fall back down, they have to give away that energy. So they absorb energy to jump up, and as they jump back down again, they have to give that energy away. Now that energy they give away will be in the form of a photon. And again, depending on the size of the energy jump, depends upon the energy of the photon, but the energy of the photon essentially is its colour, its frequency. So you can make a line spectra for every element that's gaseous and excited or given energy, and you can make these line spectra, for example, that might look something like that, an orange one, and then maybe a blue line down here. So this is the emission spectra for an element. And every element has got its own one. Apologies, that should be emission spectra. So, because we can do this on Earth in the laboratory, take a gas, excite it, pass it through a prism in order to spread out its light to see the colours that it's made of, then we can look for that pattern now inside an absorption spectrum. So for example, if these ones matched, which they don't particularly, then I could say that this element must be within this this element that produced this emission spectra must be the same element which absorbed those same energies of photons in order to make the black lines in the in the absorption spectra. So when the star emits the photons, some of those coloured photons get absorbed here and here, but then I can match those to emission spectra that I've made in my lab, and where I find a match-up, let's say for example this was sodium, although it's clearly wrong, if I then find those lines within a absorption spectrum, then I know that that gas in there must be some sodium, for example. So this idea of emission and absorption spectra enables us to find out what elements make up stars. The reason we can work out what's in the stars is because each star produces a unique pattern of absorption lines. We can match those absorption lines with emission lines from elements that we've excited in the laboratory, and therefore by matching the emission lines to the absorption lines we can work out which element or elements are within a star.